Thank you everyone for taking your time to come to this QuantBridge Applied Quantitative webinar series. And I'm so grateful for the organizers of this, Kingsford, Vanessa, and Danny, for inviting me to discuss this canonical DID, just introduction to the DID. And so this is very important for policymakers, for researchers that are just coming up, trying to look for ways to evaluate policies. That is very important for policy implication, because in economics, we know we are interested in how we evaluate programs to know where to put our money. We know resources are very scarce. So this is very interesting. Okay. And so I did this type of webinar last year where I was just focusing on the rudiment of causal inference. In that slide, when you check my website, you can see the slides available there. So I will be referring to some of the things there as a first stage if I need to. However, like Kingsford said, I'm going to make it so simple, intuitive. Let us forget about the math now, just to think about how we can evaluate programs in a way that we can make causal claims from statistical analysis without doing a lot of like structural models. Okay, so this is more or less a reduced form part. Okay, so the workshop outline is me introducing what is DID and the reason why we need it, the counterfactual framework, the standard DID to two-way fixed effect, the identification and the recent advances, even though I'm not going to be the one to talk about this. Senior facilitator are going to discuss that, an example of that, and then looking ahead what we're going to expect in the next round of this, just thinking about how we can implement this, not talking about theory alone. Okay. So let us get started. This is QuantBridge, and this is a DID workshop. And the motivation for this is just to build the theory and identification. Why is causal inference very important in applied micro in today's world? And the second part of this, we're going to do a little bit of software implementation, maybe Stata or HAR. I think that will be something we're going to welcome. Somebody messaged me, primarily asking me, are we going to use real data? And I said yes. So we are going to try and see how we can implement that. So we are going to open this to the audience to see what they are going to be interested in. Okay. And so why difference in difference, and why do they want me to like discuss this today? It is most widely used quasi-experimental method. When you look at the last slide that I explained, there is this document posted by Goodsmith Pinkham, where all of the recent research in the top 5 mostly use DID. So you are learning this for something that is going to advance your career, hoping one day you're going to publish in top 5, the QJs and the AER. That is going to be very interesting. So having this knowledge is very important. It is something that is very, very valuable in high-ranked journal, okay? So that is very important. And very, very important when RCTs are invisible. We know RCTs are the best, the gold standard. When you have randomized control trials, you can interpret your parameter as being causal. However, it is not always visible. It's very expensive. At times, it is not ethical, and we're going to talk about that. And so we have to think about clever way of making causal claim when we don't have the RCTs, okay? And so this is very, very natural fit for policy evaluation, even when we don't have when we don't have randomized control trials. So very, very important. And also very important for development economics. I know this webinar is not about development economics alone, but very applicable for development economics, which I think most of our audience are coming from. And so today's goal is just like introduce you to the canonical DID, and that knowledge enough is okay for you to write a paper for sure. You can write a paper from just DID without the advanced one. I'm going to talk about the weakness of DID and when you need the recent advances in DID, but there's a lot of paper you can still use the standard DID for, and you can still get them published. So this is a very important knowledge to have. Okay, I'm going to talk a little bit about the recent advances, but that is not my goal for today.
Yeah, sorry for interrupting. It looks
Yeah.
like they can't, I mean, I can't see your slide. Have you moved it?
You can see my slide? No.
No, we can see the cover page.
Wait.
Sure.
Can you see this now?
Nope.
Oh, wait. What's going on?
Sure.
Can you see it now? Is it moving?
No, I think you can restart sharing your screen and let's see if,
Okay,
yeah.
I stop sharing. And so let me start sharing again. Mm, can you see this now?
Yeah, so we missed all, all that, but it's good now. Yeah.
Sorry. You missed this?
Yeah, thank you.
Oh, I'm sorry. Yeah, because but we have like yeah, I'm sorry. I'm going to share the slide. So can you all see this now?
Yeah, we
Yes,
can
it's
see.
working now.
Oh, okay, thank you. All right. And so let us move forward, not to waste time. So the question is, what is the fundamental question in causal inference? Like, why is it important? Why is it that most of these papers are going to top five? The QJs, AER are, you know, more about causality. So why? Why is it very important? Okay. And so the basic question and the workforce of regression analysis or any research is to regression, right? And then you start up from this equation one that I have, which is telling me that y is a function of x, right? Whenever y changes, X is the reason why, okay? And so there's a lot of problem with equation one, even though it is the starting point, okay? You might be interested in the effect of education on wages, like the higher level of education implies higher level of wages, or the effect of health insurance on mortality. You can just run the regression. You're going to have a coefficient of beta, and then you interpret it. But we have a problem here. The problem here is that the regression in equation one is just a correlation, not a causation, because there's a lot of factors that is causing our dependent variable here to change apart from x. And so if we attribute all of the changes in y to x, we have a lot of problem, right? Because a lot of things is moving on at the same time, right? We don't have the ceteris paribus, even though the OLS try to like approximate the true beta as much as it can. There is a lot of problem, okay? So beta here just captures association, like the movement between y and x. It can be negative, it can be positive, but it is a correlation, okay? And so there is a lot of confounders that explain why that it's not being captured by hex. So if we attribute changes in y to changes in x alone, there might be a problem. Okay. For example, we are going to talk about it. For example, you want to look at the effect of education on wages, right? It might be that those who went to school have this inherent ability to do well, irrespective of education. Even if they did not go to school, they have this ability to learn any skills and do well. So if we attribute a lot of increase in wage to education, we might overstate the effect of college. So what we want to do there is, what is the true effect of education on wages while we hold all other things constant? And that is where causality comes in. But equation one cannot do that for us, okay? And so the simple comparison fails when we are comparing those who went to school and those who did not went to school, because they might be different. Like some people never went to school and they're doing fine in life, okay? And so the simple comparison between the treated and untreated is a problem, okay? And don't forget, in RCT, we are trying to compare apples to apple and then looking at what changes in terms of the treatment. And so there is this major thing we call the selection bias. The selection bias might be that those who have higher ability are sorting into going to school, and that higher ability is what is causing their wage rate, their income to rise at the end, and not really education, or maybe we are overstating that. And so equation one has a lot of problem in terms of making causal claims, okay? And that is why we need DID to solve this problem for us, so we can see the true effect of education on wages, or the true effect of health insurance on mortality, okay? And so that is the problem that we are setting out, and the reason why we need causal inference. We are just trying to look at the true effect of a program. It might be a training program, it might be health insurance, it might be just having road in your community. What is the true effect of that on the outcome you're interested in, without being overstating that, okay? So that is the problem, and we are trying to solve it. And what solves it for us is DID. Okay, so the difference in difference will do that for us. So it is very important for us to understand what DID does and how it solves the problem for us. Okay. Also, back to DID, we have to start with what we call the potential outcome framework. And I'm going to explain the reason why in the slide of my lecture in last year. I have it break down because I have a lot of undergrad in that section, but I'm going to go through it now and then refer to some of the examples. Okay. Now, this is the potential outcome framework by Robin 1974. Okay. So let us assume we are interested in an outcome. Okay. Why high one implies that that person received treatment. In this case, maybe went to school, receive education. Education is a treatment. And y high zero implies that person never went to school. They never received the treatment, which is education. Okay. So if we want to look at the effect of education on, let us say, wages at the end of the day, you're going to look for that same individual when they went to school, and that same individual when they never went to school. Okay. But that is not possible, right? Is it possible for you to have education and not have education? It is not possible for anyone to take the experience of going to school away from you, right? So that is the fundamental problem of causal inference. Actually, that is the best because you want to observe the same world. We want to look at the world where you went to school, you have all of this training, and then you want to look at the effect on wage rate. And then we want to look at the other world where you never went to school and you never had this training. And then we can look at the effect of you going to school, which is the Y high one here, minus when you never went to school. But the problem is when you went to school, you already educated, you cannot become non-educated again. So we cannot observe this star, which is the treatment effect of education on outcome of interest like wages. And so that is a problem of causal inference. So we have to have a method, a clever method of cloning that counterfactuals. We are trying to find a way to clone you in a way that we can find a clone you when you never went to school and a clone you when you actually went to school. And then we can look at the difference between the two of you and see the true effect of education on wage. Okay, so that is a problem, and that is why we need to find a clever way of solving this problem. Okay, and so we know that individuals are unobservable, like we cannot just observe just one person in the true world, and that is why most of the time in DID we talk about average treatment effects. Okay, so you want to have estimation, you cannot just run a regression on one observation, so you have to have like average treatment effect. In this setting, you are looking at a lot of people that have this treatment minus a lot of people that never have this treatment, and then you can difference both out, and your effect will be average treatment effect, okay? And so the effect for a randomly selected person from the population, and the reason behind why we say random, I'm going to explain later, but let me just say it now. Randomization implies we are trying to compare apples to apples. We are trying to compare someone that went to school and someone that never went to school. And the only difference is just the treatment, the education. And across all other things, they are the same. That is the meaning of randomization, okay? In this setting, we are trying to make sure to approximate the randomized control trials as much as possible. And so we can have different type of estimates depending on your sample size, depending on the type of data that you have. You can have average treatment effect on the treated. When you have that data, you can actually estimate that, okay? You can also have the average treatment effect on the untreated, which is your ATU, okay? But averagely or generally, the DID typically recovers the average treatment effect on the treated. That is the best we can have. We can also have just the average treatment effect. And why this is important and how it differs, I'm going to talk about it later, okay? And so these are like the coefficient that you can recover from average treatment effect, depending on your data, depending on your setting, and depending on your population of interest, okay? Now, like I said earlier, the gold standard is the RCT. What do we mean by the RCT? It is called the randomized control trials. And why is it called the randomized control trials? This is usually used in medicine, okay, where they are trying to test the efficacy of drugs. So what they do is to randomize people to the treatment group and the control group, okay? And so what they do is they give the treatment group the actual drug that they are trying to propose, and they give the control group usually the placebo drugs. The reason behind this is you might have like a headache and you get the placebo drug. Just by the virtue of taking in the drug, you might feel healthier, just like psychologically you feel healthier. And so what they do in RCT is to test the efficacy of the drug, give the people actual drug, give some people the placebo drug, and then look at the differences, okay? And that is where randomized control trials started from. In economics, it's very popular. We have a lot of papers, pioneered by a lot of economists, also the Nobel laureate Esther Duflo doing a lot of research. In Africa, looking at the randomized control trials, like randomizing people to have computers in classes and randomizing people not to have computer and looking at the effect of computer on educational outcome. That is an example of randomized control trial, but they are very expensive, like we know. Now, why is randomized control trials the gold standard? Because in randomized control trials, the level of bias is equal to 0. You are randomizing people. So the treatment group and the control group are similar across observable characteristics. So let us say, on average, they are going to have the same age, the same, let us say, a family background, the same economic and social outcome. And so the only thing that differs is the treatment in this case. So you can attribute the effect of the program, in this case, computers, on educational outcome on computers alone, because you've randomized the treatment group and the control group. But we don't always have that, okay? And so we come back to normal regression or the DID. But the DID in this setting, there is some bias that is inherent in that. And let me talk about the bias and how we can solve that. And so what do we mean by bias? Bias is a situation where your treatment group are being contaminated by people that will either do well at the end of the day. For example, you want to look at the effect of having access to mental health treatment facility, which I have in my job market paper, right? So you have to be very clever because some people might select into that program. And for them to select into mental health treatment facility program, they might have more knowledge. And when they have improvement in health outcome, it might be that the knowledge that they have is what is driving their health outcome and not the mental health treatment facilities. So in this setting, you want to remove bias as much as possible. You want to reduce the bias to be equal to zero so that you can attribute the outcome of interest to the mental health treatment facilities. And this selection bias is very, very common in normal regression. Even in DID, if you don't know the setting very well of the research you're doing, or you don't know your data very well, you might actually attribute your treatment to something else that is not your treatment. And so what we are trying to do here in DID is to make sure we are comparing apples to apples, and the changes between them can be attributed to the treatment. And so the way we do this is to make sure that the selection bias is equal to zero. We want to make sure it is equal to zero. Most of the time, it is not usually equal to zero. And that is why in a lot of DID paper, you have what we call uh, um, the robustness checks, okay? The robustness check just to make sure when you change your treatment, when you use different sample, your results still hold or still stays the same. And so what we are trying to do here in DID is to make sure we get close to the randomized control trials as much as we can by reducing the selection bias. The goal is to make sure the selection bias is equal to zero, and so that the parameter we have in the DID is going to be the same thing as the parameter we have in the RCT. Not always possible, but we can approximate that. And so the problem with DID to start with is the selection bias, and then we are trying to make sure we are solving that. And DID workforce helps us to do that. And how? We are going to make sure we expose you or expose ourselves to how DID does that. And so we can interpret the parameter from a DID estimate as being causal, okay? And so a DID is an example of what we call quasi-experiment, okay? Like we said, randomized control trial are just pure experiment. Like you're experimenting, it's like a laboratory. You are putting people to the treatment group and you're putting people to the control group. It's like a laboratory experiment. So DID is a quasi-experiment. We are trying to make sure we get closer to RCT as much as we can, even though we don't have this treatment group and control group, being assigned by ourselves. We are trying to like leverage on some things that can make us approximate the RCT as much as we can, and that is why it is called the quasi-experiment, okay? And so in this setting, you're going to have a control group. You're not the one that designed it yourself. Maybe something naturally, also call it natural experience. Something maybe natural disaster happens, and in some places they receive maybe this flooding, and in some places they never receive the flooding. And so you can say people that receive the flooding are the treated group and people that never receive the flooding are the control group. So that is a quasi-experiment. You were not the one that put people in the treatment group and you're not the one that put them in the control body. The natural experiment creates that for us, and it's a quasi-experiment. It will not be as perfect as RCT because there might be some differences in people that live in areas that are susceptible to flooding or not. Okay, so you have to find a way of controlling for that so that you reduce your selection bias and make it equal to zero. Okay, so the EID is an example of quasi-experiment, and how do we estimate it? So I'm walking you through how we can estimate that now. So the starting point is for you to have a DID, you have to have like a control group and a treated group. Don't forget again, we are trying to approximate the randomized control trials. And randomized control trials, we usually have the treatment group and the control group, okay? And our outcome variable here is Y. Let us say, mortality rate, it can be educational outcome, it can be wage rate, it can be any outcome you're interested in, okay? And so the simple difference is you want to look at, let us assume the health outcome of people living in places that have been affected by flooding. You want to look at their outcome after flooding comes in and difference it from their outcome when flooding never come, the outcome before and after, okay? And so you look at the difference, which is the difference in average outcome in the treated and control group, okay? Now, the outcome of interest is D here, okay? It is sufficient in a randomized control trials, like you randomize people to treatment group and into control group. So the difference here can be attributable to being causal because the only thing that differs is only the treatment, because the treatment group and the control group are being randomized. There's no partiality, right? So across all of the observable characteristics, they are going to be similar. So the only difference you're going to be seeing is the treatments, can be attributable to the treatment. Now, this is sufficient if you have randomized control trials. However, in a quasi-experiment, the treatment and the control are not often comparable, okay, before and after, right? I gave an example earlier, an example of the flooding, right? Some people are very smart. If you're educated, you want to like rent or you want to build a house in a place, you're going to do your research and your research like, oh, this place have an history of having flooding, so I'm not going to buy my house here or build my house here or rent, an apartment here. And those people with no level of education might not want to do any research, and they can just go to places where there might be flooding. It might also be cheaper. So just you comparing places that have been affected by flooding with places that are not affected by flooding is a problem. It's a bias to start with. And so you cannot interpret the outcome at the end to flooding because you have this selection bias before flooding comes in. And so using your quasi-experimental experiment, this equation here is not a treatment effect. It is not a true treatment effect because there is this biases that is contaminating your treatment effect, in this case, D. And so difference in differences helps us solve that, when you follow all of the assumption, and I'm going to walk you through how it solves that and how you can use that, okay? I hope we are on the same page. And now let us go to the difference in differences. I hope I have been able to convince you or illustrate why we need difference in difference. Don't forget again, we are starting from the randomized control trials, which is the best, the gold standard. However, it is very expensive. We cannot do that, okay? The next best thing we can do is quasi-experiment, okay? But the quasi-experiment, we cannot just compare the treated and control because there is some selection bias. And for us to be able to approximate randomized control trials, we want to reduce the selection bias to be equal to 0, right? And so the knowledge of DID does that for us, right? If you're publishing your paper, you send your paper to top journals, that is the first thing they're going to check. And if your parameter is being contaminated or has some bias, they're not going to accept it. So DID helps us, and you have to do it the right way. And that is why you are learning this method, okay? Like I said again, it's very common. We have other methods, the regression discontinuity, we have the instrumental variables, we have the synthetic control. We are not going to go there. This knowledge alone is enough for you to write paper and publish, okay? And so why do we call it difference in difference, okay? It is difference between two things. So what we are trying to do, don't forget again, approximate the RCT, and we are trying to make sure we are comparing apples to apple, and so that any differences we see between the two apples can be attributed to the randomized control trial, to the treatment. And so what you're going to do is to look at two groups. You are looking at the groups that receives the treatment, okay, before and after. So look at this. This is the DID estimate. You're looking at the outcome of people that lived in places that have been affected by flood, okay? And so this is their outcome after, okay? And this is their outcome pre. So in this case, you're just focusing on those who are living in the flooding area alone, okay? So that you can look at, you're not being partial here. You're focusing on them alone. And again, you come back and compare those who are not living in places being affected by flood, okay? And you look at the differences. And at the end of the day, you're going to difference those who are being affected by flood from those who are not being affected by flood. The difference between the two can be attributable to being causal. Why? In DID, the levels I'm going to show you in the figure later, the levels, we allow for these two groups to start from different intercepts. Okay, they can start from different intercepts. However, they must be trending on the same trajectory, and any changes you're going to be seeing can be attributable to the effect, in this case, flood. And so you can see here, we are trying to focus on the treated group alone and differences, what is changing between them, and then focusing on the control group and what is different between them, and then you can do the differences. And so in this setting, you can attribute your DD to being causal. I'm going to show you how in the next slide, okay? And so here we can just do a simple difference. This equation is the same thing as what I have in the last slide. And so here is just you doing normal calculation without using any regression. You can actually use just normal calculation in outcome of interest, and then just differences between your treatment after they receive the treatment and then before, and then just do normal calculation without doing regression. So this is the starting point. You can do that and have your estimate, but for now, we know we are going to go to regression. You have a lot of numbers of observation, but if you have just little numbers of observation, you can do this and you can still have your beta DID, which is the parameter of interest, okay? And so what does the beta DID here does? This measure whether increase or decrease in the outcome of interest, okay, is being caused by the treatment, in this case, flood, right? And so it actually represents the true causal effect because you've removed the differences between the treated group and the control group. You've removed what makes them different. You're trying to reduce the bias. For example, I said the treated group can have higher level of education, they can have higher level of income, and that is why they are, sorry, the treated group can have lower level of education, they can have lower information. That's why they are staying in these places that have this flooding. And so you're trying to make sure you're comparing within groups that are similar, and then you compare after, just to remove these differences, and so that we can compare apples to apples, and then you can have this true effect at the end, okay? And so this is called the parallel trend assumption. I have like a graph showing that later, and I have like an equation for that. So what do we mean by parallel trend assumption? What we are trying to say is that the treatment group and the control group in DID might start from different starting point. Like some people might be richer than the other, but they must be going in the same direction and the same slope. And whenever you see the differences between the two of them, the differences must be caused by the treatment, right? Because without the treatment, they will keep going on the same trajectory. The results are going to be the same. And so the only thing that differs is the treatment. Okay, so let us build the intuition together. So what we are trying to do here is to compare changes over time between the treated group and control group. Don't forget, we are comparing, we are checking within the treated group, looking at the differences, comparing within the control group, doing the differences, and then doing the differences. So what we are trying to do is to difference the differences between the treated group and control group so that we can compare apples to apple, and so we can attribute the result to the treatment, okay? And so why does this work? This removes time invariant difference between groups. So what this implies is that over time, things improve. For example, gross domestic product, like income. Even if the treatment never comes in, things are going to be improving, right? So you want to be making sure your outcome of interest is not being affected by these differences that just happen as a result of time. For example, people grow old, right? Without you changing anything. You want to make sure you are removing these things that just change over time that can be affecting your outcome of interest so that you are not attributing the changes to something else. So you want to remove that, okay? The second one is to remove the time trends. As time goes on, you see these changes in outcome of interest that you're interested in. You are making sure you're removing that. And so what is left is the variation in your treatment. Some people receive the treatment and some people never receive the treatment, okay? And so the setup is, 2x2 DID. You have two groups, which is the treated and control group. And then you have two periods before the flood comes in and then after the flood comes in, okay? Now, treatment occurs between the period is the period before the treatment comes in this case, the flooding, okay? And so when you do that, look at this table here. We have the control group, which is A minus B. We have the treated group, which is the C minus D. Don't forget, most of the time, the after variable are usually greater than before. And that is why when you do the treated group, you do D minus C, and then the control group, you do B minus A. And the difference between the two groups can be attributed to being causal, okay? And so that is the normal 2x2 DID setup, okay? However, this is not always visible because we still need to have regression. Why do we need to have regression? We need to have most of the empirical micro, you have a lot of observation. So, this might not be visible, but this is just to build the intuition of what are we differencing out. What we are trying to do, again, don't forget, is to approximate the RCT result. We are trying to remove the bias, and we are trying to compare apples to apple, and so that the difference in the outcome of interest can be attributable to the treatment alone. And then in that regard, we can interpret our parameter as being causal rather than correlational, and then we can make some causal claim, okay? Now, this is just me breaking down the DID framework in a formal way. Okay, so let us just walk through this. We are going to be using a lot of dummies or dummies here. So this last equation here, okay, can be decomposed into what I have here. So let me just walk you through what I'm doing here. So here we are looking at this is expectation. Expectation means average, right? Like I said earlier, average treatment effect. And so we are looking at the outcome, okay? When you receive treatment, when D equals to 1, all right? And when the post period equals to 1, when these people receive the flood. So this is the treatment. The treatment comes in, the flood. Post period, this is after they received it, okay? Minus the outcome of interest when these people receive the treatment and then the post period, okay? And you're minusing that away from the control group. They never received the treatment post. And so you can see D is equal to 0 here. They never received the treatment post. And then when they never received the treatment post. Now, in this case, the effect here can be attributable to being causal because now you're just differencing out what is different between the treatment and control group, and what you have left is the treatment term, in this case flood. I was using the example of flood. Okay. Now, in this case, we are going to have the group fixed effect and the time fixed effect. When I show the two-way fixed effect, I'm going to explain what that means better, and how that can kill some of the other variation that can be affecting our outcome of interest. And so we can interpret our parameter to being causal. Now, this is the parallel trade assumption that I've been talking about. And so, like I said, we have the treated group. Treated group can have higher intercept than the control group. They can also have lower intercept. I was using the example of flood, right? So in this case, they might have lesser wage or lesser income or lesser education level. So they can also have lesser level of outcome of interest. And so in this case, they can also be below the blue line. So, we are agnostic about the starting point. The most important thing is that they are moving in the same direction before the treatment comes in. You can see that they are moving in the same direction. And what this is telling us is that if the treatment never comes in this case, flood, okay, or flooding, if it never comes in, you can see that the red line will keep going on like this, okay? And so the only thing that causes this red line to go up, to tilt up, is the treatment, in this case, flood. It might be education, it might be health insurance, okay? You can see, you can attribute this difference that goes up to being causal, because in the counterfactual, in a world where when this group never received the flood, or this group never went to school, it's going to be the same. And don't forget, again, the fundamental problem of causal inference is we cannot observe these people in these two worlds. So we are trying to use other group as a control to see what is going to happen if these people never receive the treatment, and what is going to happen when they receive the treatment. So the counterfactual here is telling us that when this group never receive the treatment, it's going to keep going this way. And the only reason why this tilt upward is the treatment. And so you can attribute this style as being causal, or the effect of the program. Let us assume there is some region that receive, let us say, free maternal and child health care policy, and you're looking at the effect of that on, let us say, under 5 mortality. So any changes in under 5 mortality can be attributable to this style, because the only changes is because they received this FMCHP. If they never received it, this is going to keep going straight. So this is a parallel trend assumption, and this is the starting point in the DID, okay? You must satisfy that. If you do not satisfy your parallel trend assumption, you cannot interpret your parameter as being causal, okay? And how do we test this? There's a lot of ways for us to test this. One popular one is what we call the event study, which I'm going to show later, and how to, how this is going to be significant or not, okay? Now, let us go to the two-way fixed effect regression. So you can do your DID in a two-way fixed effect regression. Why is it important? Because there is a lot of papers that has like 10 million observations. It is very difficult for you to just do the calculation between treatment group and then the control group and do the differences. You cannot do everything by hand. And so the regression really helps us to solve that problem. When we have 100 million observation, 200 million observation, this is the starting point, and then you can do that, okay? And so don't forget that the two-way fixed effect looks like the normal equation one, the regression. But the major reason why this is different, and the reason why they call it a two-way, is you can see my equation one has only high, okay? My equation H here, which is my two-way fixed effect, has two subscripts, right? High, which is the individual, and the T, which is the time, all right? So two ways going by individual by time. And so you have your constant, you have your treatment, and then you have your post, right? And so in a two-way fixed effect regression, what you're interested in, your parameter of interest, is looking at the treatment and post, okay? Don't forget you are comparing between the treatment and control group, right? And so here you're comparing when these people receive treatment high and then in post T. And so these interaction times give you your DID estimate, okay? And so why can we interpret delta as being causal? One, don't forget, like I said, we are trying to compare apples to apple. And when I was trying to explain the introduction to this, we are trying to control for a lot of things. Time invariant difference between groups. We are trying to make sure things that are not different over time across groups, we are making sure we are differencing that. For example, some people just have high ability, okay? And high ability pushes them to live in places that are not being affected by flood. We want to make sure we are differencing out that inherent ability on the outcome of interest that we are interested in. And so B controls that for us, okay? And also the common time trend, there's something that just improves over time, even if you did not touch it, okay? We are making sure that is not contaminating our outcome of interest. So by stipulating that in the equation, we are removing those factors that can change our outcome of interest. And so when we remove that, what we have left is only the variation in the treatment and control. And in this case, the treatment here is either you receive flood or not, and then in the post period. And so when we remove this time invariant difference and the common time trend, we can interpret our delta as being treatment because we've observed those kind of differences between the treated and control group that might make them want to live in a particular place, or they might, that might make them want to go to school or not. Okay. And so delta can be treated as interpreted as a treatment effect or the average treatment effect on the treated. And so we can interpret delta as being causal. Okay. So that is the starting point. Okay, that is the starting point. And so this is very important for us to have causal estimate. However, there might still be some problem. For example, there might be some things that cannot be controlled for by the beta and gamma, and that is why at times in a lot of regression you have what we call conditional and covariate. For example, you can control for age, you can control for level of education that can make these people want to stay in some particular region. And when you control for that, you can see in some regression, you have something like X beta as well. You can control for that and you can say conditional on this covariate, this is my average treatment effect, okay? And so one powerful thing that we can also do here in the two-way fixed effect model is when you have panel data. Very important. Like when you have a panel data, that is, you can follow people over time. Like this, you have data on individuals and you can follow them across years. Okay. When you have this, the fixed effect is very, very strong. So when you have your fixed effect, which is your unit fixed effect, that is, you're controlling for individual fixed effects, okay, like this time invariant characteristics like genetics and ability, you're controlling for that. And the time fixed effect controls for things that are just changing over time. Let us assume in this case, maybe GDP increasing over time that might be affecting people's preferences or maybe affecting where they live. When you have a panel data and you're having this individual fixed effect or the unit fixed effect and you're having the time fixed effect, that actually kills a lot of other variation that can be explaining why. And you can actually interpret your parameter effect as a true treatment effect. But we know that panel data are not usually available as well. But when you have it, you are doing you're going to be having a very good estimate attributing your estimate to the true treatment effect. Okay. However, it is not always possible to have panel data. We can go into the problem of having a balanced panel or imbalanced panel, but panel data helps us a lot in making causal claim once you have the unit fixed effect and the time fixed effect. Okay. Now, like I said, I've explained this adding covariates. Okay. Like I said, equation 8 and 9 might also not be perfect. You might also want to make sure you are controlling for a lot of characteristics that might help you reduce standard error or making sure your treated and control group are comparable across what you can see. For example, in your data, let us assume you have level of education, and you know that level of education can actually affect where people live. You can just put that in the regression so that you can make sure other variation that can be explaining your outcome of interest are being killed by that, and you can interpret your parameter as being causal. I think I have some question coming up in the chat. Can I answer them, or you want me to finish first, Kingston?
Yeah, I think you can finish and then we can have some 10 minutes for
Okay.
those.
Yeah,
Yeah.
I'm checking my time so that we can just finish. Okay, so this is just the formal statement of parallel trend assumption. I'm not going to go there, okay? But what this one is telling us is that the parallel trend assumption is telling us that before the treatment and control, before the treatment comes in, the treatment group and the control group must be going on in the same direction. And what this one is telling you is that this is the treatment group and this is the control group, okay? The difference must be equal to 0. You can see, this equation and this equation are the same thing. So this is when D equals 1 implies this is the treatment group, this is the control group. Before the treatment comes in, they must be the same. So the difference between them is equal to 0. If it's equal to 0, whenever you see any difference after the treatment comes in, you can attribute it to being causal. So that is kind of like the mathematical notation for that. But this is very crucial for your interpretation, for your causal interpretation. If you do not have parallel trends, don't forget we are trying to mimic the RCT as much as possible. And parallel trend assumption makes us be sure that we are approximating the RCT. If you do not satisfy this assumption, it's very difficult to make causal claim. You can make causal claim conditional on your pre-trends, but here you have to satisfy that, okay? And so one of the major things or one of the major tools that is being used to look at the parallel trend assumption is what we call the event study specification. And what does event study specification mean? It is the same thing as the two-way fixed effect, okay? But what this one is just telling us is you can see here, we are looking at the dynamics of the outcome of interest before the treatment comes in, okay? Before the treatment comes in, and you're going to have your relative period, in this case, most of the time, -1 before the treatment comes in up to your post period. In this case, you're looking at the treatment group, comparing them to the control group. You have to omit -1 for normalization. In normal dummy regression, we call it the reference group, right? And so in that regard, the pretreatment, the difference between the treatment and control group can be positive, but should not be statistically significant. Can be negative, but should not be statistically significant, okay? For you to have a causal claim. This inspects, maybe we have parallel trends, or this also explains that we are comparing apples to apples. Maybe people living in places that have been affected by flood and people that are living in places that have not been affected by flood are similar across other things, okay? We are just trying to make sure we are comparing apples to apples. We are trying to make sure, again, that we are approximating RCT as much as possible. And so I'm going to give an example from my job market paper. And so what I'm doing here, and one of the major problems I have is, in my job market paper, I have 3 major estimation. And the first one is looking at, so my job market paper is about having access to mental health treatment facility and mortality related to mental health. And so my identification strategy is around the within county variation in access to mental health treatment facilities, which is, you can call it just a major two-way fixed effect. And if you look at it, there's a lot of variation between counties that have access and counties that do not have access. And so I'm leveraging on these within county variations to look at the effect of access to mental health treatment facilities on the outcome of interest, okay? However, there might be some problem with that. What is the problem? It might be that people who are living in places that have access to mental health treatment facilities might have higher level of education, right? It might also be due to local market condition. For example, let us assume Amazon shows up somewhere. These mental health treatment facilities can respond to that by creating 10 mental health treatment facilities, right? And so the counties that have more mental health treatment facilities might be different inherently from the counties that never have mental health treatment facilities. And so even though I'm having effect, it is still correlation. Even though I'm having a lot of inverse probability weighting, I'm having a lot of controls, right? However, it is still very difficult to make causal claim, okay? And so one unique thing or one clever way that I try to solve that is to pick, for example, 2 counties, okay, over 5-year period before. And so these 2 counties never have any new mental health treatment facilities in this period of years before, okay? And so 5 years before, and so I was able to see county that received just 1 increase in mental health treatment facilities, okay? And so I am interpreting that to being exogenous. I'm interpreting that to be random. I'm interpreting that to being to not being affected by local market condition. For example, let us assume Amazon shows up. You would expect that mental health treatment facilities that will show up will be more than 1, okay? So here in this map, I'm just comparing counties with just 1 increase in mental health treatment facilities with counties with no increase in mental health treatment facilities. So here I'm saying these counties are similar across other things. The only difference is some county received 1 and some counties never received at all. And I'm assuming that one is just being exogenous because know, they might just pop up for whatever reason. And so that is why I have this subsample in my paper, just focusing on event study, just to make sure my result has or satisfy these parallel trends. Okay. And so this is how event study looks like. You can check any area, any QJE paper, event study looks like this. They might have different design, different aesthetics, but this is usually how they look like. Now you can see I'm comparing counties 5 years before they receive mental health treatment facility. You can see -5 to -1 is my pre-period time here. And so this is how to interpret event study. You see these vertical bars, because they are touching this red line, it implies that they are not significant. For example, you can see that they are hovering over the zero line here, right? Which implies that the difference between the treated county and the control county at zero, okay? Fine, you're seeing, you can see in this setting, some are lower, some are higher, but statistically, this is zero. It is not significant. If you look at the difference between the treated group and the control group here, the difference are not significant. So here, this is an example of where parallel trend assumptions are being satisfied. For sure, you check a lot of other papers, the event study might look very, very, better than this in terms of you see some event study where this pre-period term are just on this zero line entirely. That is a perfect event study. But the takeaway here is that taken together, the difference between the treatment group and control group are not going to be statistically significant. And in this case, they are not because they are hovering over this, okay? And this is my normalization, -1. And after some county received mental health treatment facility, you can see how mortality drops, okay? You can see, you can attribute these differences to the mental health treatment facilities. You can attribute it to this county receiving this facility because before they receive this, nothing is happening, nothing is changing. The only thing that makes this goes down is because some counties now have mental health treatment facility, okay? And so this is an example of testing parallel trend assumption and making causal claims, okay? So we're gonna come back to this in question and answer, but that is what I have. The other assumption that I have to be satisfied is what we call no anticipation, okay? For example, what do you mean by no anticipation? Actually, having anticipation in your model or in your setting or in your research can actually affect your parallel trends. For example, let us assume that I was giving an example of free maternal and child healthcare policy, which is a pilot program in some states in Nigeria where they received free maternal and child healthcare policy, free maternal and child healthcare. And this is administered in this way. Free care is given to mothers once they confirm their pregnancy till 6 weeks post-delivery, and treatment are given to kids from birth to 5 years. Okay, so let us assume some mothers are knowledgeable about this policy. They can actually move from the control state to the treated state just to like receive this free care. And so what we are trying to say here is we are making sure there is no anticipation. Nobody knows about this, or even if they know about this, they are not moving to where they're going to get benefits. For example, in my event study, we can say there is no anticipation because nothing is happening before these people receive mental health treatment facility. When you have anticipation, it's going to bias your result and it might also show up in your event study, okay? So you have to also satisfy no anticipation for you to have causal estimate, okay? The next one is what we call the stable unit treatment value assignment. In this assumption, what we're trying to say is that the treated group are not being contaminated by the control group. For example, let us assume I was given an example of some students receiving computers and some students not receiving computers in secondary school setting. Now, you want to make sure that the students that receive computers are not sharing that computer with those who are not receiving computers in the control group. For example, let us assume we have two brothers. One is in the treated group, one is in the control group. So the one that is in the treated group went home and was using this computer and was sharing it with the brother, okay? It will contaminate your results. So it's going to be biased because now the control group are also receiving the treatment and it's going to, like, in this case, bias your result downward because you're not going to see the true effect of the effect on computer on academic outcome. So here, for you to be able to make causal claim, you have to make sure your treatment group are not being contaminated by the control group and vice versa, okay? And this is all about the time fixed effect. Very, very important that the treatment group and the control group are receiving common shocks. Like in this case, you're making sure these are affected Similarly, they are moving on the same trend. It's not like, one is going up, one is going down. You have to see like a particular pattern going up to the treatment, and the only thing that is differencing between these two groups is only the treatment. So you want to make sure these two groups are receiving common shocks, and the only thing that differs is the treatment to the treatment group and no treatment to the control group. Okay. Now, this is the staggered treatment timing. I'm not going to talk about it. I just provide it in the slide. You can go back to it. I know Professor Dente is going to talk about it very, very deeply. And I will just preview this. This is very recent because, before 2016, you have your two-way fixed effect results, you have your DID result, you publish it. Now, there is going to be a huge problem if your treatment is staggered. For example, the FNCHP that I was talking about, I actually have it in this slide before, but I removed it. Why? Because the treatment was staggered. We have the phase one and the phase two. In that regard, you cannot just do a two-way fixed effect. If you do a two-way fixed effect, your results are going to be biased. Why? Because some group are later treated and they are controlled before they become treated later on. And so when you use your two-way fixed effect, it's going to be biased. Okay. And so that is why you need the recent DID, the Son and Abraham, the Goodman Bacon, the Callaway and Santana, the popular ones. However, I'm just trying to talk about the disadvantage or where your DID estimate or your normal two-way fixed effect might not work. Normal DID, normal two-way fixed effect is going to work when you have just single treatment timing. In this case, for example, my event study, everyone received treatment at once, 5 years after, okay? And that is it. Let us assume they received this treatment at different point in time, then my two-way fixed effect might be biased. I have to use maybe the Son and Abraham, okay? So you have it in this slide. You're going to learn about it in the second round of this. Okay. And these are the recent one. You can just go back there because of time. I will not go there in depth. Okay. Now, practical recommendation, like I said, DID knowledge is enough for you to write a causal paper, and you have all the right to publish in top journals if your treatment is just one time, and then you have your treatment group, you have your control group. Okay. And so the general practice you're going to do if you want to like start a paper is you have your data, just plot it, plot the raw trend, see what is going on. Okay. There might be some issue with your raw data that you don't know, and there might be some interesting relationship that data or your plot might be is very correlational, but from there you can see some kind of like interesting pattern going on. For example, I was talking to a professor yesterday and we are talking about something that is very interesting. And so we're talking about policy such as the Medicaid increasing reimbursement from home care. And so what they do was to plot home care before that policy comes in and after. And you could see that the level of home care just went up immediately after the policy comes in. That is still correlational, but that is something that gets you going. Oh, is this going to be causal? Okay. And then it's next thing you want to do is to test parallel trend at this state that received this reimbursement rate that goes up. Are they similar across the outcome that I'm interested in? You do that. And then if the treatment just comes in one, you can use your two-way fixed effect. If it is staggered, then you go to this Son and Abraham and the recent one. Okay. And so one of the major problem with reduced form that we have here, or the DID, is because we are just looking at the effect of the treatment on the outcome of interest. So the problem here is we never know the reason why we are seeing changes in the outcome. We are just saying, oh, these people received education, their wage rate goes up, right? What is the reason? What is the explanation? The reduced form never shows up that. The DID will not tell us that. So you have to be smart to think about, oh, what might be the other thing that is explaining our outcome of interest? And that is why mechanism comes in. It might be, oh, maybe these people, when they went to school, they are getting special training on how to get jobs. And so you go ahead and check schools that are preparing people for job market, and then you can plot that and say, oh, this is the mechanism behind the result that I'm saying, because the reduced one will never do that for you. You really want to think about it and say, what is this treatment effect and where is it coming from? In DID setting, most of the paper in DID, you're going to be looking at you're going to be seeing a lot of mechanism explaining your result, because the DID itself will never do that for you. You're just looking at the effect of the treated on the outcome of interest. Okay. So we have this classic example. Please, if you're interested in DID causal inference, you have to read this paper as a starting point. you have to read this paper as a starting point. Very easy to like understand. This is just a normal, very rigorous DID where they are comparing the minimum wage and employment in two states, New Jersey and Pennsylvania. Please, you have to read this paper. Because of time, I will not go in there, but what they're trying to do here is to compare minimum wage, okay, between the treated group and the control group and see what happens to employment, okay? I'm not going to go there in the interest of time, but please read this paper. It is very interesting. It is very interesting, and it's going to get you going and really understanding this DID. Okay. Now, common pitfalls to avoid. If you have pre-trained, you can publish for sure. You can publish in lower level journal. You cannot publish. You have to make sure because once you have pre-trained, you are not approximating RCT. You're not. It's very difficult to make causal claim. Okay. You cannot just use two-way fixed rate blindly without understanding what is the policy. Is this policy? So, for example, the reason why in the FMCG paper, me and my co-author used the Son and Abraham was because we understand that, this policy is staggered. So two-way fixed rates will be biased. You can report it as a robustness, but that should not be your main result. So you have to understand the context of where you're doing your research. You cannot just, pick data and run your regression, okay? You can have a lot of controls and say, conditional on controls, this is my causality, okay? In my previous slide, talk about interpretation of this parameter. You interpret it normally. The standard errors, the lower standard error means you are going to have higher significance coefficients. Okay, and so in the second section, we are going to be doing a lot of application, but we are going to discuss how that can go. I will be flexible about that and what the audience wants, but we can discuss that. And also, these are recommended resources. Please, mostly harmless. You have to read it. You have to read it for you to, be conversant with this. You can just say, hey, because I came to this workshop, now I can do research. No, you have to read this. You have to read it. You have to understand it. You have to understand, and we have Scott Cunningham, very supportive. He's come to my school. This book is very important. A lot of examples are Python, Stata, where you can just, start. And also we have a lot of other resources that, Scott Cunningham has the mixtape, podcast. I listen to it, every time. And this is very interesting. You can subscribe to that and listen to them. And this recent paper are going to be discussed in the other section by our senior professors, okay? And so the key takeaway here to summarize is that difference in difference removes the bias if you do it the right way. And so if you remove the bias, then you can actually interpret your coefficient as being causal, and you can approximate the randomized control trials, the gold standards, as much as possible. Make sure you are testing for parallel trends. It's very important for you to like publish higher. And in standard treatment, two-way fixed might not work, and then you're going to learn those in the upcoming lectures. Okay. And so DID is very important and very useful. And if you have papers where you can use DID alone, you can actually publish. And I know, everybody in this workshop are interested in publishing. You're not just here into pastime or to waste your time. You really want to be a successful researcher. And if you do it the right way, you can publish in a very high level journal. Thank you so